Hi students, welcome back to another session on electrostatics. So in the previous classes, we have learnt the basic characteristics of charges and how the charges interact with each other. That is, in the case of Coulomb's law, we saw the force between two charges, then force between multiple charges. As we saw in Coulomb's law, when two charges are placed separated by a distance, there is a force on each other. Say there is a charge Q here, capital Q, and I'll place a charge small q at a distance, say r, assuming that the medium is air. Now you know that the charge Q will have a force acting on it, which is according to Coulomb's law. Of course, 1 by 4 pi epsilon naught capital Q into small q divided by r square. That will be the equation. Same way, exact same force will be acting on capital Q due to small q also. So each other, they exert force on each other, and that force can be either attractive or repulsive based on the nature of the charges. If the two charges are opposite kind, that is unlike charges, that is one is positive, one is negative, then the force is attractive. If they are like kind, that is both are positive or both are negative, then the force is repulsive. All those things you understood in the previous classes. Now, say in case if I remove one of the charges, I mean if capital Q is not there, if this charge is not there in this region, if I remove this off, then do you think there is a force on Q, small q? No, there won't be. Only any another charge in the surrounding can exert a force on this charge. So therefore, if I remove capital Q, then there is no force on small q. If I remove small q, then there is no force on capital Q. It is very clear. Now, the moment I remove this charge Q, then what is left out here? What is there at this point? If you say it is nothing, if there is nothing, then the moment I place small q here, then there is a force acting on it. How can that happen? If there was nothing at that point, then what exerts force on this small q? So to understand these characteristics of this region here, the early scientists, they said, if you don't place the charge also here, the presence of this capital Q in this region has done something to this medium. So at this point, you cannot say there is nothing. There is something here, and that something is given a name, field. We say that there is electric field here. So today's topic is electric field. So what is electric field? A region surrounding a charge in which another charge experiences a force, we can say. Now I will call them as, this is the charge which is it is causing the field around, let us say, and this charge small q, I am going to use it to test the effect of capital Q. So I will call it as test charge. Usually test charge is Q naught we take, that is 1 coulomb, positive 1 unit of charge we say, that is a test charge, or unit positive charge we call. Now let us try and understand what is the field at any point around a charge. Now basically, what is electric field? A region surrounding a charge where a test charge experiences a force is said to have electric field. So in this region, there is electric field if you place a test charge, it should experience a force. Place a test charge at some point surrounding, some point near you. If there is force acting on the charge, then it means to say there is some field in that region. Now, electrostatic force means electric field, of course. Same way, like you have learned even for other gravitational force, magnetic force, etc. in your previous studies, earlier studies, that is, this object, this mass experiences gravitational force. Due to what? Due to Earth, we say. Earth causes gravitational field in this region. In that field, this small mass chucked is, this experiences a force, downward force, that is gravitational force. So same thing here also. One charge causes the electric field. In that electric field, another charge experiences a force. Now, other than this cause, the charge which I use to test the presence of the field, that charge is called as test charge or unit positive charge. So now let us just understand in detail something about this electric field, the strength of it, etc. Strength of the electric field at a point is denoted as electric field itself. So instead of saying it as electric field strength, just electric field is also fine, and that is denoted by E. Like F is the force, E is the field here. Now think of two charges, same thing. So capital Q, small q. So small r is the distance between them. What is the force between them? So you know that it is K into Q divided by R square. Now if I place this small q here, the force is so much. If I don't place this small q, then what is left out is electric field, and that electric field is given by this much. So there is no small q. Without that, what is left out is electric field here. Same way, small q also causes electric field. If you remove this capital Q, surrounding small q also there is electric field. In that electric field, when you place this capital Q, it experiences a force. This small q will cause electric field at this point. How much will that be? Of course, F is equal to K in E is equal to K into small q by R square. It will be. That's all. The distance is same, of course, between the 2 points. So therefore, field will be K into Q by R square. Now, from these two equations, you can understand that E is equal to, say, E is so much, F is here. If you divide this F divided by this test charge Q, then you are going to get this one. So you can write it as something like this. Now if I take small q as Q naught test charge, then electric field at a point can be defined as the force per unit charge at that point. So what do you understand from this? It's very simple. If you want to find the field at some point in a region, then place a test charge there. On that test charge, whatever the force acts, that force per test charge is called as electric field strength or just electric field. Now test charge is 1 coulomb, therefore force per coulomb, that will be the unit of electric field strength, that is Newton per coulomb. Force per charge, that is Newton per coulomb. So what is the definition? So the definition is for electric field, definition of electric field, what is that? Electric field at a point is given by the force experienced by a test charge placed at that point in that region. So definition is very simple. The force experienced by a test charge or a unit positive charge placed at a point gives the electric field at that point. So that's the definition. So force per unit charge is called electric field. So electric field at a point is given by the force experienced by an unit positive charge placed at that point. Its SI unit is Newton per coulomb. Yes, so as I was telling, the force at this point Q naught due to capital Q is in what direction? Assuming that both the charges here, of course, as positive, I can say the force is in this direction. So force per unit charge is the electric field. So how do you get the electric field? E is equal to F by Q naught. But in the vector form, of course, this is nothing but E as a function of R is equal to F as a function of R divided by Q naught. Both are vectors, of course. So then, what is E? E is equal to 1 by 4 pi epsilon naught Q divided by R square and R cap. So if the force is in this direction, the field also at this point should have been in the same direction. So force and the field are in the same directions. So this is the vector form of electric field at a point. Now let us try and understand what will be the field at a point. When I say field, it is the electric field strength I am talking about. So an electric field strength unit also you understood, Newton per Coulomb. So electric field at a point due to a system of multiple charges. So let us assume that there is a charge Q1 here. This is causing the field. This is not a discharge. This is causing some field. So around itself. Now at some point P, what is the electric field of this charge? At some point P, the electric field here is, say, E1. Q1 is causing an electric field E1. Now what is E1 by definition? E1 is equal to, same way, 1 by 4 pi epsilon naught Q1 by R square, simple. So E1 is equal to 1 by 4 pi epsilon naught Q1 by R square. What is R here? It is a distance of that point P from Q1, and that distance I will represent it as R1 here, therefore it is R1. And if I take this as the distance vector, the direction vector R1, then electric field is E1, it is a vector here. So when I just put the direction, this will be R1 cap. This is the electric field at point P. Now if I have another charge, say somewhere here, if I have another charge somewhere here, say Q2, which is at a distance R2, and the direction vector is also in the same direction, Q2 to P, then this also causes electric field here, which will be, say, E2. Then what will be E2? Almost same, with only magnitude and direction different both. So Q2 here, R2 square, R2 cap. So this is the electric field due to second charge. Now as you all know, whether it is an electric field, electric force, any other kind of force, whatever vectors you take, so when you add them, you have to use parallelogram law of vector addition or triangle law of vector addition. That is superposition principle. The principle of superposition of these two vectors gives you the resultant. So let me just get the resultant here. This is the resultant at this point. The resultant of E1 and E2, the sum of these two fields is in this direction. So I will call it as, say, E dash I will call. Right? Then if I take one more charge, say there is another charge, for example somewhere here, Q3. If there is another charge Q3, then that charge also causes a field. Say direction vector is R3 and the field is in this direction, E3. E is vector of course, E3. Then what will be the net field at P now? E1 due to Q1, E2 due to Q2, both added up to give E dash. Now that resultant E dash should add up to this, once again parallelogram law of vector addition. This is resultant E double dash I'll call, whatever. So this is sum of these two now. So automatically E1, E2 and E3 together gave this electric field. This is the resultant electric field at a point due to a system of three charges. So due to a system of three charges, what is the electric field here? Net field E resultant is equal to E1 plus E2 plus E3. This is the net field. Add up. Of course E3 also same as I told you. E3 is equal to 1 by 4 pi epsilon naught Q3 by R3 square. R3. So if you just substitute and add up, what do you get here? 1 by 4 pi epsilon naught is common, right? What is left out now? Q1, Q2, Q3 divided by R1, R2, R3 squares. So Q1 by R1 square, R1 cap, correct? Plus Q2 by R2 square, R2 cap, plus etc. So this is the net field. For 3 charges, of course 3 terms will be there here. What about n number of charges? If you have n number of charges, let me just write it here. The net electric field due to n number of charges, n number of point charges, of course. Ideal case, point charges we take always. So when the distances are more, any distributed charge can also be considered as a point charge. I have already told you that. So net field at a point will be, so E is equal to E1 plus E2 plus E3 plus E4 etc. like that up to En, which will be that equation which I have shown there. So what will be the 4 pi epsilon naught? Then I'll take summation here. Then what is the term? Q1 by R1 square into R1. So Qi by Ri square into Ri cap, where I is equal to 1 to n. Recall when we took force expression, force on a charge due to a system of multiple charges. So force on one charge due to a system of multiple charges, when we took, almost same equation was there, but there was I is equal to 2 to n, remember that, because one charge on which you are finding the force due to remaining charges. So total n number of charges, in that on one charge you are finding the force due to n minus 1 number of charges there. But here it is the field at a point due to all the charges, so n number of charges. So therefore you get this equation. This is the electric field at a point due to n number of charges, and directions is according to the resultant, of course. So that's about electric field. Thank you.